All right, let's go ahead and get started. Lecture 4. Just a heads up, I decided it would be a good idea to forget my little adapter for my microphone, so I'm hoping the audio comes in okay for our recording today. A little housekeeping. So first off, attendance grades are up to date. Because of the way that we set up homework 1.1 in here, it's already graded. The solution is now posted. I'm going to pull up Blackboard here in a second to sort of show you how that's going to be organized in future assignments and whatnot. Homework 1.2 was due today. How'd that go? The two triangles and the unit conversion shouldn't be that bad, right? Pretty straightforward. Okay. Homework 2.1 is going to be assigned today. This is going to be the first assignment where there isn't like a timed quiz on Blackboard. The way it's going to work, there's going to be a homework assignment, and you're going to upload a scanned PDF. And that's how the rest of the assignments are going to go this semester. So again, you can put like a cam scanner on your phone or Microsoft Lens on your phone or something like that. Or if you have a tablet, you want to do the problems on the tablet and then upload those calculations, that's fine too. Whatever method, as long as you're uploading your calculations in a neatly discernible format and whatnot. One thing I did want to mention is the SAME ASC student chapter is having an event tomorrow at 5 p.m. in this room. They've got free pizza, cornhole, and some games and whatnot. So I'm sure they'd love to have you there. And if any other engineering student organizations have any events that you want me to advertise them, just let me know and I'll put them on the slides like I'm doing this. Let me pull up Blackboard before I move on from this because I wanted to make sure that I caught that. So if I pull up the student preview, let's see. Okay, so what you should now see on Blackboard is a couple other folders. So the first thing, I think I already showed you this one, is the older homework assignments. What I'm going to do is whenever homework assignments are graded, I'm going to stick the actual assignment in this folder right here, so that way to sort of keep the course shell like organized. Otherwise, it'll just be oodles and oodles and oodles of assignments all on that main page. But solutions to previous homework should now be visible, and you'll see homework 1.1 solution. And so if you click that, what you'll see is both the assignment and the solution in one spot. So you can see, like, here's the assignment. What I did is I took the quiz that was on Blackboard and just put it in this PDF. And then here's the solution. So that way you have something to go off of. And I'll do that with every assignment so they're all in one spot. Okay. Does that sound good? Okay. All right. And that'll be sort of how we organize things throughout the class. Okay. Did everybody get the QR code? Okay. All right. So today what we're going to do is begin our first real topic in the class. Last week was mainly just a review of both math and physics fundamentals that I think are necessary to negotiate the class. Now let's actually start talking about Engineering 213. Our first main topic of the class, which is what we're going to be looking at for the next couple of weeks, is what's called the statics of particles. And when we use the term particle in here, what we're really talking about is a concurrent force system. Particle is a lot fewer, it's fewer syllables, so it's just shorthand for that. A concurrent force system is any situation or any scenario in which all of the forces all meet at a common point. And so we call that a concurrent force system. A non-concurrent force system is when they don't meet at a common point. And so we use the term rigid body analysis for that. So if we're talking about statics of particles, we just mean they all meet at a common point. And so we're going to be spending quite a few lectures on that. That's traditionally where statics starts, because you need to walk before you can run, and statics of particles is a natural first step. This course is founded on the bedrock principle of understanding what vectors are. And we're going to start at the basics of vector manipulation, vector addition. We're later on going to be doing vector multiplication, two different ways of doing that, by the way. But today our methods are going to be very graphical, and we're going to rely on trig. We're going to take this and generalize it a little bit later, but let's go ahead and just sort of jump right in. Okay, so we talked about this a little bit last week, but I want to sort of formalize this today. As I've mentioned, this course is, if you wanted to give a general description of both this course and Engineering 214, which you would take next semester, it would be defined as a study of forces. And forces are going to be the main star of the show for pretty much everything that we do this entire semester, is looking at forces. I mean, statics deals with scenarios involving forces where things sit still, and dynamics deals with forces and scenarios where things accelerate. Now, in order to define a force, we're going to need to express its magnitude and direction, and that's where vectors come from. In math, we have two primary concepts that are related to this, and those are scalars and vectors. Now, scalars are any type of mathematical object or expression that contains just a magnitude. So when I say scalar, I mean a number, okay? There are physical quantities that relate to that. So for example, mass is a scalar term. Temperature is a scalar term. Temperature doesn't really have a direction, you know? If I asked you how warm it is today, you wouldn't say 80 degrees to the east. It's just 80 degrees. There's no direction associated with temperature. There would be a direction associated with wind, right? If you ask somebody how windy it is, they'll say, well, maybe the wind is 20 miles per hour north by northwest because the wind is blowing that way, right? So wind would, if we're talking about wind speed, it would have a magnitude and a direction. Right? So scalars are any mathematical expression that contain only a magnitude, but vectors contain magnitudes and directions. We use vectors to represent things like velocity, things like acceleration, and forces. Okay, and so forces is going to be, at least at the very beginning, that's what we're very interested in describing. Okay. Now, a couple of properties of vectors. Okay, so first thing I'll mention is notation. If you open up your textbook, you will see that vectors are represented by bold letters. Okay, so you'll see, like, for example, if there was a force vector, it'll be represented by a bold F. Okay, now it's very difficult to write a bold F using handwriting, so we typically will write vectors with like F with an arrow over it, or F with like a caret over it, or something like that. More often than not, I'll write it with an arrow over it. But we are going to be pretty diligent in here to ensure that whenever we're referring to vectors, that we are referring to them with the proper notation. And I'll actually get into what I mean by that today in our example, because we're going to be looking at a resultant vector, and whenever we write the letter R with an arrow over it, we're referring to the vector. But if we write the letter R without an arrow over it, we're referring to the magnitude of that vector. Okay, so we are going to be pretty diligent in making sure that we're writing things appropriately, because it'll help in understanding what we're doing. Okay. Now, if we're looking at a graphic definition for what a vector is, we generally define a vector by 3 data points. Like I said, we have the magnitude and direction, but we also have a point of application or a point of origin. So let's say, for example, let's just keep things simple. Let's say I have a hook or a nail in a wall or something like that at point A, and I have a rope attached to point A, and I'm yanking on that hook or that nail with a 10-pound force. So I have point A, where the force started. I have a magnitude of that force of 10 pounds at an angle of 30 degrees from some reference axis. Okay. One of the things that you will see is that vectors are typically drawn to scale, at least at the onset of a course where we're first trying to understand what vectors are. To be blunt, as we get later on in the semester, we might be a little fast and loose with that. But for now, we're going to try and draw vectors to scale. So like the idea is this is a 10-pound vector. If I were to write a 20-pound vector, I would draw it twice as long. Okay, so that the length of the vector is proportional to its magnitude. Okay, it's like engineering 102 all over again, all that engineering scale stuff. Remember that? Fun stuff, right? Okay, so far so good? Okay, all right. So vectors, by that logic, can be scaled. Like I said, if I go back to the previous slide, if I have a 10-pound vector and I draw it on a sheet of paper and I want to draw a 20-pound vector, I'll draw it twice as long. Well, more generally, you can take a vector and multiply it by a scalar and it will increase its magnitude. What it will not do is change its direction, except if you multiply it by a negative number, you'll flip it, but it'll stay along that same line of action. So like, for example, if I have some vector p, okay, and I take that vector and I multiply it by 1.5, what I would get is this vector. It's along the same direction, it's just its length has been, or its magnitude has been increased by 50%. If I were to take p and I would multiply it by -2, what I would do is I would get a vector that is twice as long, so the absolute value of its length is twice as long. It's just going in the opposite direction. In fact, if we have a vector and we want to express what is the magnitude of that vector, we actually use the absolute value sign because it's kind of what we're talking about. So if this is p, -2p is twice as long, it's just flipped in the other direction, okay? We're not like rotating it, it's just staying along that same path. So far so good? Okay. So our first task in this course, and when we talk about the statics of particles, what we are talking about, really the main crux of our skills between now and our first celebration of learning is going to be revolved around adding vectors, okay? So in other words, if I have a point and I have a series of vectors going through that point, how do we add them together, okay? Because where this is going to tie into statics is like if we're talking about statics of particles, the first thing that we're going to try and figure out is if I have a series of vectors, how do I add them together? And then the second thing I'm going to try and figure out is, okay, let's say I've got all these forces here. Let's say I know what S is and I know what P is, but I don't know what Q is. What does Q need to be such that point A is in static equilibrium, so that point A doesn't move? Okay, that's going to be sort of the second thing that we try and figure out is what does force Q need to be to keep point A in what we call static equilibrium. We'll define what static equilibrium means a little bit later. Now, like I said, what we're going to be dealing with for this first couple weeks is what we call concurrent force systems. Again, concurrent force system, that's a mouthful, so I'm going to shorthand that to mean the term particle. And all I'm saying is any physical situation where all the forces all meet at a common point, okay? Now, what we're going to do in this class is we're going to start by learning how to add two vectors, okay? And we're going to do a lot of this graphically with like trig and law of sines and law of cosines. Then we'll progress, instead of adding just two vectors together, let's add n vectors together, like, you know, a bunch of vectors together. But we'll, again, walk before we can run in here. Okay, so far so good? All right, now, if we have, so a couple rules about this, and this I think should kind of make sense. If we have vectors that are along the same direction, if they're all acting the same way and through the same point, we can combine them by just adding their magnitudes. So, for example, if I have, let's take a look at this tug of war competition on the bottom right, okay? So let's say everybody on the blue team, okay, they're all applying a force to the rope along the same direction. They just might have been applying it with different magnitudes. Let's say, let's just come up with some numbers. This guy's applying 60 pounds, this one's applying 80, this one's applying 70, this one's applying, 100, this one's applying, 30, whatever, right? If we wanted to figure out what is the total contribution of the team, because they're all applying forces through the same point, maybe we'll call that point in the middle of the rope, right? All of the lines of action of those forces are all going through the same point. If we wanted to find the contribution of the team, just sum up all the different forces from all the different team members, right? Okay, and then the idea is that the purple team, they're doing the same thing, right? And so if this system of forces at the blue team was applying more force than the purple team, then the rope would move that way. Make sense? So when the forces are equal, that the rope just sits there, right? That's the idea. Okay, so far so good? So if I use the term line of action, what I'm referring to is that path along which the force is acting, okay? So in this scenario, all of these folks playing tug of war, they're all applying force along the same line of action, which is why we can just add them up. If they weren't along the same line of action, then we couldn't just add them. We have to be a little bit more careful about how we do that. Okay, so let's talk about a scenario like that. Let's talk about a scenario. Let's take vectors P and Q. Now, P and Q are not applied along the same line of action. P, for example, is going this way, and Q is going this way. Okay, so the way that we do that graphically is we just apply that in a tip to tail fashion. Okay, so the idea is if I have, let's say I have vector P and vector Q all going through a common point, what I can do is I can move those vectors to where we start with vector P and then vector Q. The start of vector Q starts at the end of vector P. I'm a popular guy. I will have to call you back. And so the idea is that we can sum vectors by stacking vectors on a tip-to-tail fashion. So if I wanted to find, if I had vector P and vector Q, the sum of those vectors would be it would start at the very beginning and go to the very end. Okay, and we can do this for 2 vectors, or we can do it for a bunch of vectors. For example, if I have 3 vectors, P, Q, and S, P plus Q would be from here to here. P plus Q plus S would be from here all the way to the very end. Okay, and don't worry, we're gonna have an example here in a little bit where we go through this process, and you'll see what I mean. Now, the big thing about vector addition is that vector addition is commutative. Okay, now commutative is a very fancy way in mathematics of saying that the order of operations doesn't matter. In other words, if I have 2 vectors, P and Q, the idea is that P plus Q is the same thing as Q plus P. Okay, same operation. So first, does that make sense? I'll give you an example of what I mean by that. So let's say that I was on the corner of 20th and 3rd, right, which is right down here, right? And let's say I wanted to go to the far end of Corley Hall, right? One way of doing it would be going down 20th and across 5th, or I could go down 3rd and up Hal Greer, right? I could go this way and that way, or I could go this way and that way, right? And so the idea is that P plus Q is the same thing as Q plus P. And in the end, what is the sum? The sum is that distance from 20th and 3rd to the corner of Corley. Does that make sense? It's the same idea. So we can do vector addition in a commutative fashion. We'll get the same answer. Now, this is not true with vector multiplication. Well, I'll qualify that. There's actually 2 types of vector multiplication: dot products and cross products. Has anybody heard of these before? So cross products, they are not commutative. The order of operations does matter, but we'll do that later. We'll get to that later. So far, so good? Okay. Well, let's do an example, okay? So let me pull this up in the notebook here. This is what we're going to focus on today. We're going to use a graphical and trigonometric approach to find what we call the resultant of the 2 forces applied to this hook shown. So let's talk about what a resultant is. So I have a hook and I have 2 forces applied to this hook. I have a 600 Newton force and a 900 Newton force. And they are each applied through the same point, but at different orientations, and they have different magnitudes. Now, what a resultant is basically saying, okay, I got a bunch of forces. I don't want to deal with a bunch of forces. I want to deal with one force, okay? Just one, okay? And that force is the resultant. And the resultant is basically defined as the sum of all those forces. So instead of 20th and 5th or 3rd and Hal Greer, I just want the straight shot, okay? I just want a single vector that can represent both of these forces. And so I want the sum of these vectors. So what is the resultant? It's the sum of these vectors, okay? So far, so good? So replace these 2 vectors with one vector. For that one vector, I want to know what its magnitude is, and I want to know what its direction is, okay? Sound good? All right, so let's take a look at how we would do that, okay? And so I want to do that using a somewhat graphical approach. Now, let me show you how we're going to do that. All right, so okay. All right. So we're going to do this in a, like I said, this tip to tail fashion. And I'm going to do my best to try and draw these vectors to scale. Okay. Now I'm going to do it with the 900 Newton vector first, then the 600. We can do it either way. It doesn't really matter. I just picked one and you'll see what I mean here in a second. Okay. So I'm going to start off with this 900 Newton vector. Okay. So what I'm going to do is maybe down here, I'm going to draw myself a little coordinate system, maybe something about like that. And I'm going to draw myself a 900 Newton vector. And I'm going to try and draw it to scale. So when I say to scale, what I mean, I'm going to assume this is 900. So when I draw the 600 Newton vector, I'm going to draw it a little bit shorter. Okay. Everybody with me so far? So this is, put a little arrow there. That is a 900 Newton vector. And let's just make sure we're all paying attention. What is this angle right here? This angle. 30 degrees. That's that 30 degrees right there. Okay. $30 degrees. So far, so good? Okay. Now, so that's going to end at this point. What I'm going to do right here, I'm going to draw myself another little coordinate system right here. So I'm just sort of putting like an X and Y axis right here so that when I start drawing vectors and I start labeling angles, that I kind of have like a frame of reference here. Okay. So now I did the 900 Newton vector. Now I'm going to do the 600 Newton vector from this point. Okay. And so the 600 Newton vector is going to look something, I'm trying to draw it to scale based on this diagram. It's going to look something about like that. And maybe it's only about this long. Okay. So I'm trying to draw it a little bit shorter than this one. Maybe I'll do that again. Maybe I'll make it a little better. Let's see. Let's try a little better. That's probably good. Okay, so I got this right here. 600 newtons. Okay. All right. So far, so good? All right, so let's see if everybody's paying attention here. Okay, so help me out with something. What is this angle? This angle. 75 degrees. Not 45, it's 75. See why I drew that little coordinate system there so we can kind of see that? From the horizontal axis up there, it's 75 degrees. Okay. Okay. And by the way, let's be clear. What I did was this one, then that one. If I had done this one, then that one, I would have gotten the same. I would have gotten from, like, what I'm trying to do is figure out how far it is from here to here, right? Whether I do the 900 and the 600 or the 600 and the 900, I'd have gotten to the same point. Everybody okay with that? All right. Now, let's see if we can flex these geometry muscles. Let's see if we can figure some stuff out. I am curious. Can somebody identify for me what this angle is? What is this angle right here? 30 degrees, right? How did you do that? Parallel line, cut by a transversal, right? So, right, because I've got a, what do I have? I have a line, a diagonal, right? So if this is 30 degrees, that's 30 degrees. Remember that? Okay. So there's that. How about Let's do another one. I'll do this one in black. Let's do this black. How about that? I need to put arrows on these. Okay, what about that black angle? Somebody said something? 105, right? Now, how do we get that? From this part right here, that entire semicircle is 180 degrees, right? That's 180 degrees. So if this is 75, that makes this 105. So far, so good? So that makes this angle 105. Okay. All right. Everybody with me so far? Here's what I'm getting at. What I'm getting at is this, okay? What I want to do is I want to see if I can apply those lovely trigonometric relationships that we practiced in the last homework, okay? So maybe what I can do is I can say, all right, I have a triangle that looks like this. All right. So what do I know about this triangle? So what I'm trying to find is this right here. This is the resultant from the beginning to the end. What do I know about this triangle? Well, I know that this side has a length of 900 newtons. I know that this side has a length of 600 newtons. Now, somebody help me out. What is the measure of that angle? 135, because it's 105 from here to here and another 30 from there to there. This is 135 degrees. See what I'm saying here? Is this now we've got a triangle where we know three quantities. We've got to solve for the other three. Let's see if we can figure some stuff out here. Now, before we move down the rabbit hole, I want to sort of go back to this part right here. And my scale is way off. Just bear with me, okay? Remember, what is this angle again? What is that angle? 30. When we apply the law of sines and the law of cosines, the law of sines and the law of cosines is going to give us this angle. This angle, I'm going to come up with a Greek letter for this. We're going to call this alpha, okay? So my trig relationships are going to help me solve for alpha, but I want to keep this 30 degrees here in mind. Just bear with me on that. Okay. So far, so good? It's just a fact we're going to employ later. Now, let's take this triangle and let's start dealing with this resultant. Now, how do we define vectors? Vectors contain two things, a magnitude and a direction, right? So now here's a triangle. I know this side, and I know this angle. If I want to find this side, is this a law of sines problem or a law of cosines problem? Law of cosines, right? Because what I've got is I've got a situation where, you know, here's the triangle, right? Let's just put a little triangle right up here. My little thought bubble here. We have a triangle. We know this. We know this. We know this. And we're trying to find out that, right? And so I propose the magnitude of R we can find using the law of cosines. Now, a little bit of notation. When I write R, just R by itself, that means the magnitude of the vector. Okay, so if I ever write R without an arrow over top of it, I'm referring to just the magnitude. Okay. Now, how am I going to do that? Well, what does the law of sines say? What does it say? It says something like c squared equals a squared plus b squared minus 2ab cosine c. Isn't that right? So maybe what I ought to do is say that R is the following. It's 900 newtons squared plus 600 newtons squared minus 2 900 newtons, 600 newtons, cosine 135 degrees, and then the square root of all of that. You see how I did that? It's just the law of cosines just applied to this triangle. I know this, know that. I need to find this side. And so I'm just taking this and taking the square root of all of it. Okay? That means we got to break out the Casio FX115 ES Plus or similar scientific calculator. All right? And what are we getting for the magnitude of R? I will say 2 decimal places for this. Anybody got a value for me? $1,390.57. Do I have a second on that? Okay. And the units for this are newtons. Okay. So if I wanted to characterize that vector summation, that resultant, I can characterize that summed vector with this magnitude, right? Now this is the magnitude of that vector, but it has not yet given me the direction of this vector, okay? So what about direction, okay? Well, I propose that the direction can be characterized with this angle alpha. In other words, I have a vector, and I know it's going to be pointing about like that. But what does about like that mean? Well, it depends on what this angle is. Okay? And I propose that we can characterize this by solving for that angle. And I don't see any reason why we can't solve for that angle using the law of sines. In other words, the sine of this angle divided by that equals the sine of this angle divided by that. Okay? So the sine of alpha divided by 600 newtons equals the sine of 135 degrees divided by the magnitude of the resultant. Does everybody see how I did that? Just law of sines, right? So therefore, so let's not scrunch this. Okay, so therefore, the sine of alpha equals, let's see, the sine of 135 degrees times that fraction, right? So all I'm doing is I'm multiplying both sides by the 600 newtons, okay? And when you chug this out, you get something like 0.3051, right? And what I'll then do is say that alpha is the inverse sine of that. Now, what I'm getting is something like 17.76 degrees. Anybody else get something like that? Okay, good. I saw you raise your hand too, so I think we can go with that. So far, so good? All right. Now, I wanted to characterize this vector. Okay, I want to characterize this vector. So my answer is going to be the vector equals some magnitude and some direction. Okay? So a magnitude and a direction. Let's start off with the magnitude. The magnitude is pretty easy. That's going to be 1390.57 newtons. That's the magnitude. Okay? What about the direction? Okay? So I want to be clear that what we're talking about is we're saying, okay, let's sort of think about a physical representation of this. What I'm saying is that, okay, here's the ground. Here's the hook that's coming out of the ground, right? And what I am wanting to do is replace this entire scenario with my resultant, right? So what I want to do, I literally want to erase that 900 vector, that 600 vector, eliminate that. It doesn't exist. And I just want that. And so I want a magnitude and a direction. So probably the easiest way of doing that would say, okay, here's that coordinate system. I can do better than that. Here's that coordinate system. And what I'm after is this angle. Now, my question for the class, is that angle 17.76 degrees? No, it's not, right? 17.76 degrees is measured off of the 900 newtons, but it's not measured off the horizontal. What would the angle be measured off the horizontal? 47.76, because I need to add the 30 degrees. So the way that I'll write this is I'll say 47.76 degrees, and I'll write it like that. So I'll say, here's the magnitude and here's the direction. This is the angle, and it's from the horizontal going up. Okay? So my answer is 1390.57 newtons at an angle of 47.76 degrees. And it's written in such a way that we all can interpret it the same fashion. This is the magnitude, this is the angle, from the horizontal, we go up. Does that make sense? There's no ambiguity in how it's written. Now, for those of you that have experience with IJK, I imagine some of you are like, there's a far better way of doing this, especially if you have 6, 7, 8, 9 vectors. You're not wrong, okay? We're going to take our time with it, though, because I don't want to start introducing that until we're all comfortable with the sound fundamentals, okay? So we'll get there, I promise. We'll get there quick. We'll probably start talking about that by the end of this week, so. Okay. What do you think? Sound good? Okay, let me pull up your homework assignment because I want to talk about just the format of that real quick so that we're all on the same page. So this is your homework assignment, okay? So basically what I want you to do is I want you to do what we just did for textbook problem 2-3, okay? And what I'm going to do for this week is I've literally just copy and pasted both the text for that problem and the image for that problem on Blackboard, okay? So that I know some of you are probably still waiting for a textbook to come in the mail. I don't want you to wait on that, okay? I'm going to do that for this week. After this week, you're on your own, okay? Because we've got the holiday in between the start of the semester to after the holiday. You should be able to get your book, okay? Does that sound good? So you've got a hook. You've got the magnitude of these two forces. I want the magnitude and the direction of the resultant. Same idea, okay? Sound good? We're going to do another problem on Wednesday, which is sort of like this, but it's kind of backwards. In other words, instead of summing two vectors to find the resultant, The idea is I'm going to give you one vector, and I'm going to tell you what I want the resultant to be, and you need to figure out what the other vector needs to be in order for that resultant to be the case. Okay. So once we do that, then we'll start broaching into our IJK land. Sound good? Any big ticket questions? I'm giving you 10 minutes of your life back. I'm going to stop the recording, pull the code up one more time. You all have a wonderful day.